So today we're going to talk about how to solve problems involving the conservation of mechanical energy. So the key to this is to realize that if there's no friction in the problem, so usually they'll say frictionless, then the total mechanical energy, which is the sum of the kinetic energy and the potential energy at each point, that will be the same. So the total energy at 1 will be the same as the total energy at 2, and we can use that fact to solve a problem. If there is friction, which is a non-conservative force, then the amount of mechanical energy will change, and the amount that it will change by is the amount of work that's done by friction. So the recipe for solving these problems is to find an equation for all the energy at point 1. So I need to look at point 1 and say, is it moving? If yes, then it's got kinetic energy. Is it at a height? If yes, then it's got gravitational potential energy. Is there a spring that's compressed or stretched? If so, then there's elastic energy. So I'm going to find all the equations for the energy at point 1, all the equations for the energy at the second point, and then if there's no friction, I'll set those two equal to each other, and then I'll solve for any unknown. So let's do a few examples and walk our way through it. So let's start off with an example of a roller coaster. So for a roller coaster, there's no springs, so the only energies involved are kinetic energy, 1/2 mv squared, and gravitational potential energy, mgh. So if there's no friction, the speed at any point only depends on the height compared to where it starts off with. So the total energy at any point is 1/2 mv squared plus mgh. So let's do an actual problem here. So here we've got a 100-kilogram roller coaster, travels from A to B on a frictionless track. At point A, it's at a height of 50 meters. At point B, it's at 10 meters. If it starts from rest at point A, what's its speed at point B? So if we read the problem, it says it's frictionless. So if it's frictionless, the energy is conserved. So I know the total energy at A is equal to the total energy at B. So what's my equations? Well, we just did that on the previous slide. The energy at A is going to be 1/2 m times the speed at A squared plus mg times the height at A. So I know my m is 100 kilograms from the problem. And I know the speed at A is 0. I know the height at A is 50 meters. What's the energy at B? Well, it's going to be 1/2 m times the speed at B squared, which is what we're trying to find, plus mg times the height at B. So I know everything on the left-hand side, so I can find the energy at A. I don't know the speed at B, but I know mg and the height at B. So I know everything in that equation except one thing, so that means that it's possible for me to solve for that one thing, the speed at B. So let's go ahead and put in what we know. So mass is 100 kilograms, so everywhere there's an m in that equation, I'm going to put in 100. And you'll notice I don't have the m times v1 squared, because that's 0, because the speed at point A is 0, so I could just leave that off on the left-hand side. So I've got mg times the height at A, so 100 times 9.8 times 50 is equal to 1/2 times m times v2 squared, which is what I'm trying to find, plus mgh at point B, so 100 times 9.8 times 10. So if I put in my numbers, I get 49,000 on the left-hand side is equal to 50 v2 squared plus 9,800. So now I'm going to subtract the 9,800 over on the left-hand side. So 39,200 is equal to 50 times v2 squared. And solving that, I get v2 is 28 meters per second. Okay, so that's a problem where I just have speed and gravity. Let's next do a problem where I have speed and a spring. So now I've got a block coming in. Again, it says it's a frictionless surface. It hits a spring and it's brought to rest. So this is like an example of maybe at the end of a subway track, they have a spring there in case the brakes don't work to stop the train. So the 1,200 kilogram car comes along at 18 meters per second, no friction, so that means the total energy is the same. And then the spring is compressed by 2.2 meters and the car stops. So let's say at point 1, is where the thing is moving, and then point 2 is where it's compressed the spring in by a distance of 2.2 meters. And V2 is 0. Okay, so what's my energy at position 1? Well, my energy at position 1, I've got kinetic energy because it's moving. I don't have any gravitational potential energy because it's on the surface. And I don't have any spring potential energy because the spring is not compressed. Okay, so each point I'm going to look at the 3 types of energy and say, do I have them or don't I have them? At position 2, V2 is equal to 0. So I don't have any KE. Do I have gravitational energy? No, I don't have gravitational energy because it's still on the ground. But I do have elastic energy. So I've got 1/2 K times X squared. Okay, so I've got my mass. I've got my V1. I've got my X, how far it's compressed, and I don't have K. All right, so what do I do to solve? Well, what I do to solve is I set E1 is equal to E2. So if I set E1 is equal to E2, then I've got 1/2 m V1 squared is equal to 1/2 K X squared. Okay, so let's see. If I do algebra, I've got 1/2 on each side, so I'm just going to get rid of that. So that gives me X squared. Sorry, that gives me K, sorry. K is equal to m V1 squared over X squared. So let's see, 1200 times 18 meters per second squared divided by X, which is the amount that the spring is compressed, 2.2 meters squared. And I get a very big number, 388,800. And let's see, so now I've done the algebra. Let's look at my sig figs. I got 2, so that's 390,000. And the units for spring constant is newtons per meter. It's how much force is needed to stretch it by 1 meter. So it's a pretty stiff spring, which is what you'd expect if you want to stop a car. All right, so let's now do a problem where we've got all 3 kinds of energy. And I'll give you a hint. This is a very favorite kind of problem to put on the test because it involves all the different kinds of energy. So it tests that you know what you're doing. So what are the problems going to be? Well, they'll either be a problem like what I'm doing now, or it'll be one like I'm going to get you to do for the assignment. So let me go over to my whiteboard so I have a bit more room to solve this. Okay, so I've got a spring, and I didn't actually write it on here. But the spring constant is 350 newtons per meter. I'll have to edit my slide to make sure that's on there. So the spring constant is 350 newtons per meter. That should be stated in the problem. Okay. All right, so I've got a spring. I compress it by a distance of 0.15 meters, and I have a 2 kilogram block. Then the block is released, so you can see it's been over here on the left, it's been pushed back by a distance of 0.15 meters. I release it from rest at 0.1 and I let it go. So what's going to happen? The spring is going to stretch back out again. It's going to push the block away, so the block's sliding along, and it's going to reach its maximum speed at 0.2, and then it's going to slide along. It's going to go up this frictionless ramp, and you'll notice it always is frictionless, so that means that the energy is always the same, and it's going to stop at 0.3. So I'm going to have 3 places at which I have to find the energy. So let's go ahead and write here on the right, what's the equations for the energy at each point? So remember, that's what I have to do first, is write down what's my equations for the energy at each point, and then I set them equal to each other to solve for the unknowns. All right, so first of all, at point 1, what kind of energy do I have? So I've got kinetic energy, 1/2 mv squared. Do I have kinetic energy? Well, what does it tell me about point 1? It says that the block is released from rest at point 1. So V1 is equal to 0. Let's write down what we know. V1 is equal to 0. So kinetic energy at point 1 is 0. So there's no kinetic energy. Okay, does it have a gravitational energy? Well, the height at point 1 is 0. So there's not going to be any gravitational energy. The only kind of energy I'm going to have here is elastic energy. I've got an x of 0.15 meters, so I'm going to have an elastic energy at that point. So what am I going to have? I'm going to have 1/2 k times x squared. So that's 1/2 times 350 times 0.15 squared. And I can actually get a number here rather than just having an equation. My energy is going to be 3.94 joules. And again, I keep extra significant figures at this stage. All right, what's my energy at point 2 going to be? All right, so what's happening at point 2? Well, at point 2, it's moving, so the speed is not 0. I don't know what it is. So it's going to have a non-zero kinetic energy. Is it going to have any gravitational energy? No, because it's still on the ground. So the height at point 2 is 0. So it's going to have 0 gravitational energy. And how about the spring constant? Well, at point 2, the spring is already back where its equilibrium position is, so there's not going to be any spring energy. So the only energy I'm going to have at point 2 is kinetic energy. So that's going to be 1/2 m times v2 squared. And let's see, what do I know? I know my mass is 2 kilograms. So I can say that's 1/2 times 2 times v2 squared. And I don't know what v2 is. That's what I'm trying to find in part A. So I've got 1/2 times 2, which is 1. So it's just going to be 1 times v2 squared. So I've got an equation rather than a number. Okay, and let's find what's the energy at point 3. Well, energy at point 3, what do we know about point 3? Well, point 3, it says how far d up the ramp will it travel before stopping. So it stopped at point 3. So v3 is equal to 0. So it's got not got any kinetic energy. So kinetic energy is equal to 0. Okay, what about gravitational? Well, the height of it is not 0, right? It's gone up. It's at this point here, a distance h3. A distance h3 up the ramp. So that's not 0. So it does have a potential energy of mg times h3. And how about elastic potential energy? Well, elastic potential energy, again, the spring is back at equilibrium. There's nothing pushing on the spring. So x3 is 0, and so the potential energy from the spring is equal to 0. So I know I've got 1/2, sorry, not, yeah, 1/2, no, not 1/2, sorry. I've got no kinetic energy, I've got no elastic energy, so I'm going to use the equation mgh. No half in that one. So it says m2 times 9.8 times whatever my h is, and let me put a subscript h3 on that. Okay, so that's going to be 2 times 9.8 is 19.6 h3. Okay, so now I've got equations for the energies at point 1, 2, and 3. And in fact, for energy 1, I have an actual final number for the energy. So how do I solve it? Well, my recipe says after I found the equation for the energy at each point, I just set them equal to each other to find the unknowns. So for part A, it's asking me what's the speed of the block at point A. So at point 2, so for A, what I'm going to do is I'm going to set energy 1 equal to energy 2. Okay, so energy 1, 3.94 joules, is equal to energy 2, and energy 2 is just 1 times V2 squared. So V2 squared is equal to 3.94 joules, so V2 is going to be square root of 3.94, which is 1.98 meters per second. And now I'm at a final number, so I should round to the right number of significant figures. And let's see, I'm at 2 significant figures, so that's about 2.0 meters per second. Okay, so most of the problem is just figuring out the equations for the energy, and then once you've got them, you just set them equal to and solve for what you're doing. All right, what's the next one? The next one asks for how far up the ramp will it travel before stopping? So we're going to need to find the height. So in that case, what I'm going to do is I'm going to set E1, which is a number I know, equal to E3, because I'm trying to find something at position 3. So what do I know? I know 3.94 joules is equal to 19.6 times H3. So H3 is 3.94 over 19.6, which is just over 0.201 meters. Okay, but the problem, it didn't actually ask me for the height. It asked me for how far D up the slope does it travel. So let me pull this up a little bit so I have a bit more room. And let me draw the triangle here in red so we know what we're talking about. So we've got this triangle. It's asking for the hypotenuse of the triangle, and we know the height, and we know the angle is 25 degrees. Okay, so I want to find the hypotenuse. So what do I know? Well, I know the side that's opposite. All right, so if I know opposite, I'm going to use the sine. So what I know is that sine of 25 is equal to the opposite over hypotenuse. So it's 0.201 over D. So D is equal to 0.201 divided by sine of 25, which gives me 0.48, if I round it to 2 significant figures, 0.48, and it's a distance. So it's in meters. Okay, so the recipe for solving these problems is always the same. You look at each point in the problem. If it's frictionless, you find the energy at each location, all the 3 kinds of energy: kinetic energy, gravitational energy, elastic energy, get an equation, and then to solve, you just set the energies equal to each other. So if I go back to my slideshow, the problem that I want you to do is sort of this problem in reverse. So we're going to start off with a guy letting go of a ball at the top of a hill, and it's at a height of 450 meters. The ball is going to slide down the hill. At point 2, it's going to be going at its maximum speed. When it gets down the hill, it's going to hit the spring, and when it hits the spring, it's going to compress the spring and come to stop. So point 1 is when it's up at the top of the hill, point 2 is when it's at the bottom of the hill, and point 3 is where it's compressed the spring and it's completely stopped. So what we want you to do is find what's the speed of the ball at point 2, and then find how far the spring compressed and stopping the ball at point 3. And again, if you can solve these 2 kinds of problems, the one that I did and this one here, you should be able to do any problem that you see on the test.